And we start by opening a new script, which I try to make as large as possible, so hopefully it's also easy to recognize for you. And let's start to look in the first exercise at our feedback function. We know what the feedback function looks like, and if we want to investigate the feedback function, there's two things that we need to know. One thing is the shape of the function or the mathematical form of the function, and the second thing is all the parameters in that function in order to numerically find out special properties like steady states and invariants of this function. So let's start by copying over our parameter set. If we want to look at our function, we will look at it for specific parameters chosen here. And so I copy into my script the set of parameters that is suggested in the slide number 4. In order to look at our function, we identify the function in our differential equation, and I have highlighted it in yellow. I can equally copy this, and we call our feedback, say, inhibition function, and I call it the first one because it's the first that we are going to look at, and here's my function. Now we need to be careful and see whether we can actually use it as it is. If we want to define a function, the first thing that we need is not the function, but is the variable that turns up in this function. Now, what does this function depend on? Well, it depends on the amount of the second molecular species, which is called x2. So we might call this variable, which we have to put in round brackets, x2. This is the variable that we are going to look at, and we'll see where does it appear in our function. It appears here, so we should equally call it x2 here. So now we have the shape of the function, and we have expressed it in terms of this variable that we need for the function definition following the @ symbol. So this is an easy way of defining a function, and what you can see is that this will execute the functions for the parameters given above. Now, what we'd like to do first is we want to do what does this function look like when we have our inhibition switched on. So we have a ki value which is non-zero, so it means this function actually depends on our concentration of the second molecular species x2. So you have learned this before, but I do use a function which is called fplot, which is the function plot. So any function that we have defined before, we can plot by using fplot, and we do so by filling in the name of that function. It's called fb_inhib1, so it's feedback inhibition 1. One more thing that we need to do, we need to define the range of our variable, the second molecular species, over which we want this function to be executed. And we do it simply in the interval 0 to 1, assuming that this is a good choice. This is our script completed, and we should be able, if we execute it, to get a plot of this function, and we can see the output of this function immediately plotted in a graph. I make it a little bit thicker so you can see that more easily. And you can see that this is a decaying function which starts to decay from a value of 100. If I change my things a little bit, starting from a value of 100, this is a decaying function that goes eventually to 0 for very large values of our concentration x2. So what we have here is we have now plotted our function using FunctionPlot, and we can see its features visible in this graph. We can actually make a comparison of what this same function would look like if our variable would not enter the model linearly, as it does here, x2 just by itself, but if it was taken to a power, similar to what we know from Hill functions. So if, for example, we have or I do it maybe differently. I just copy this over. If I now do the same thing and I take the case where my Hill coefficient, so to speak, Hill-like coefficient is not 1 but 2, so it's this concentration of the second species to the power of 2 or squared. Then what we can do, if we have the old plot, if we keep the old plot and we now call this new function somewhat different, maybe function inhibition 2, and we plot the second function on top of it, then we can do even a further slight modification and make it in red. Then we can see our new plot has the old function where the exponent was equal to 1. Now there's a thick blue line here. And our new line when the exponent is squared or equal to 2, then we can see that the shape of the function differs. I think this is one of the tasks that you're going to do in assignment. So you can very simply, by using function definition and function plot, get the graphical idea of what these functions look like when you change a parameter, in this case the exponent. Right? This completes our first set of example. As I say, you have the working MATLAB code also in your save. We don't just quit. Also in the downloadable materials. And we continue with our second example. Now we're looking at the steady state of our model, the steady state of the model that you can still see displayed on the left side by similarly using the function definition, but now doing it on the whole model rather than just this nonlinear feedback function. Because now we know that the model uses this function, but in the context of this cascade of two consecutive functions. So how will we do this? First thing that we'll need, again, is if we want to simulate this, we'll need the set of parameters. So I copy them again over from the model. Now we need to have a function definition as before. So we can just call it our function. Now it's a function that comprises the whole model. We'll need some variable, and we can again call it x, but we actually must consider now an array, namely x is now composed of two variables, x1 and x2, so we need to distinguish between the two. And now we want to use our function definition on the whole thing. How do we do this? If we have a set of functions rather than one function, we put them into square brackets, an array, and separate them by the comma. The second equation is actually rather easy. If you look on the left side, it's just x1 minus x2. So we can very easily incorporate this in here, x1 minus x2. So we have that set up correctly already. Our first thing must have a capital X because we have defined it as a capital X. And we can now check whether we have defined completely. We need to call everything with a capital X. So we have parameter A divided by km1 plus our feedback inhibition, ki times x2 to the power of n. However, n is equal to 1, so we don't really use it at the moment. And we have now completed it by saying minus x1. So our first differential equation, which you can see on the left side, is now completely written into our function definition. Our second differential equation also put into our function definition completely, separated by a comma from the first and taken together by the square brackets. Sorry. I want to get a new line. Now we have defined our equation. How can we solve the equation? Well, you have seen in the materials, if you have read through them, that there's something called fsolve, another function that helps you to solve for the steady state of a set of equations, because the steady state means that both differentials are equal to 0. So what we are now assuming is that in our model, all our derivatives, namely the first derivative and the second derivative, are equal to 0. And then, if we solve for the two concentrations of x, this will be the steady state concentration, namely the concentration when there's no more change in the system. So we do this by applying fsolve to our function. Our function is called f, and we need to specify not a range now, but in this case it's initial conditions. We need to assign some value for x1 and x2 such that the solver can start to approach the solution from this initial point on and get there hopefully quickly. Sometimes it's not easy to have a good guess, but of course you can try to combine it with simulations if you don't know where exactly to look. In this case it's not critical. We use this set of initial conditions 1, 1, and if I execute this I should have a solution which we can look at in our control window. Yes, we can see MATLAB found a solution which is final steady state concentration of x1, which is equal to 3.1127, and the final concentration or steady state concentration of x2, which is equal to 3.1127. Right, so this is some value, and it's whatever your units of concentration were. That could be, for example, millimole per milliliter or millimole per liter. Now, if we actually go back and look at our equation, you remember what this model looked like. Is it surprising that these two numerical values are identical? Not really, because the way the model is set up, the second equation tells you if the second equation is equal to 0, you can immediately find out that if x1 minus x2 is equal to 0, it means that x1 must be the same as x2. So in this special set of conditions, which we did by putting all rate constants equal to 1, the numerical value of x1 will always be equal to the numerical value of x2. This just as a comment for those who think it's a little bit bizarre. Typically, this will not be the case if you have rate constants other than 1. Right, so we are finished with this solution. We have found our steady state and we have predicted a value. And you can then, of course, change, for example, the parameters and get steady state values at different parameter values. So, for example, if I change the value of a to 2, I can execute this code, and you can see for a double size of the parameter a, you have a different concentration of the steady state values, and so you can do your studies for any concentration and set of parameters that you would like. No, I don't need to do this. I want to close this window because this completes our exercise.